All right. Well, hi, everybody. I'd love to introduce Rodrigo Pinto from UCLA, where he well applies causal inference to understanding the dynamics of economic systems. Welcome.
Okay, thank you very much, Greg. Thank you very much for the opportunity. Look, I prepared this presentation for a general public, and studying causality, given how many literatures there are, it can be quite confusing because the way that causality is dealt in economics is different. How people from statistics talk about causality, and it's also different from people in computer science deal with causality. They all are based on the same core ideas, but the tools that they use to actually examine causality are quite different. And if you get years ago when I started studying causality, I was indeed quite confusing from one paper to another paper and understand what they actually are doing, understand the core principles that are behind uh, what the type of analysis that they do. So I prepared this presentation that goes first over the principle of causalities, which are very simple principles. Then I go to language of causality and make a big distinction between the causality that uses structure model versus the causality that use language of potential outcomes. And language of potential outcomes is the type of language that's most used, especially both in economics as in statistics. I explain a little bit of the deficiency and the limitations of this approach. And then I go to a little bit more. I started entering the type of causality that is studied in computer science that use direct classic graph models and use specific tools to examine causality. I go even detail why there are different tools in this different language and why we need kind of tools to examine causality that are often not expressed in standard statistical or probability theory. So let's start. And I started this quote with Fritsch. And Fritsch had this interesting idea about what's causality. It was a quote in his paper in 1930 that he says that we think of causal as something imperative that exists in the exterior world. In his opinion, that's fundamentally wrong because we should think about the, that the problem of causality is essential problem regarding of way of thinking, not a problem regarding the nature of exterior world. Let me give some context about what he's saying, and what he's saying was quite deep in terms of it actually kind of change how economists and most of people think about causality. Before before Fritsch explained that causality is based on a way of thinking on hypothetical variation of input variables to determine outcomes, people thought about causality in a setup of an experiment. So they would say that they get a causal effect of one variable of another if you go to a lab and do a zillions of experiments, and you can actually verify that one variable impacts the other one when you control everything else. And then we said this tangible type of analysis of causality is completely wrong. The key idea of causality is not something that you can actually verify that is causal, but it's much more like an exercise of abstract thinking, that you're going to get a causal model that it's assumed that exists, that we are going to use theory to define the causal relationship to the variables, and then you are going to hypothetically vary one input to determine the outcome, and this way of thinking is the one that actually can define causality. Another thing that you can actually go to a lab and test if actually works. That was kind of a major uh, different of way of thinking about causality. So, and after Frisch, we come Havelmo, which is a very important economist in the causality world, and he stated that cause effects are not empirical description of variables that you can actually see in the world, observable variables, but also hypothetical description of works. How you define causality? They realize, they get insight that the causality is fundamentally defined by a thought process through models that I idealize as experiments, and you hypothetically vary variables some inputs to determine outcomes. And then we are going to see how these ideas shape how we actually think about causality and how to generate an interesting setup to examine causality and identification. Now, to start talking about causality, I'm going to use a very simple model. And the model is just y is a function of a treatment t and an unobserved variable u. I'm also going to assume that this function f of p and u is going to be a linear function. Y is going to be beta 1 plus beta 0 plus beta 1 t plus u. When I define a function, y is a function of f of t and u, I'm actually assuming causal relation between the variables, and in this case here, I'm assuming that t and u cause y. And then we have the simple analysis of causality. The counterfactual outcome ytu is I get the equation ftu, and I going to fix the values t and u to some values, which are going to be little t and little u. So I have t and u defined variables, little t and little u are simply values that these variables can take. And we say that the counterfactual outcome ytu is the variable y when the variables t and u are fixed to the values t, little t and little u. And what will be the concept of set parables? Set parables is a concept that says, hey, I'm going to hold these variables to some values, and I'm going to see what happens with the model. And that's a very simple model. Here, I'm going to get the difference between y, the counterfactual y, when I fixed the variable t to t plus 1, and u is the fixed to a value that's going to hold fixed, and I compare this counterfactual with the counterfactual in which I fix the variable t to little t. When you do this simple equation using the linear model, we get that this difference here is beta 1, and there comes the analysis that beta 1, it captures the causal effect of t and u because I'm varying t for 1 unit, and I get the equation beta 1. Okay, so then it's often the case that you see this equation here, linear equation, say, okay, so beta 1 is the causal effect of t in y. Okay, okay.
So, question at this point:
Go
you
ahead.
specifically chose linear here because the effects are independent. How
No,
does that impact your? Well, that's because it simplifies the story, but to what extent is this critical?
oh, it's not critical whatsoever. Here, I'm using linearity just to give a sense that when people use linearity, that's what is actually kind of behind their mind.
Mhm.
And that's the only time that I'm going to use linearity. Most of the time, I'm always going to use a causal model that is simply a non-parametric causal model in which the key point here is that I'm defining causal links. I'm saying that T and U cause Y. And the linearity here is just not to illustrate the fact that in this linear model, the parameter beta 1 is the causal effect of t on y. In most cases, you are going to have kind of parameter define the causal effect? You will not. In most cases, the equations are completely non-parametric, and then we are going to define the parameters using analysis that's similar to this one here, but a little bit more general. And I'm going to construct this generality in a few slides.
Okay, excellent. Thank you.
Look, now, but the key point that I use this model here is the following. There is an enormous difference between defining a counterfactual outcome. Here I'm defining the counterfactual outcome y when the variable t is fixed to little t, and the variable u, which in this case here is an error term, is an unobserved, is fixed at value 0. And for these two values, I have that the counterfactual outcome y t0 is going to be beta 0 plus beta 1 little t. It turns out that if you forget about the causality and only use the statistical property of the model, the expected value of the outcome y condition t be equal to little t is going to be beta 0 plus beta 1 t whenever t and u are statistically independent. Indeed, kind of mean independent. Now, are these two parameters have come to the same equation, but they are completely different. One here is just kind of statistical procedure that get the expected value of a variable condition other. So that's a operation of statistical conditioning. And this one here is a causal operation of fixing the variables. And when we deal with causality, we are going to use kind of the fixing operator instead of the expectation. And it turns out that in most cases, specific in this one, when t and u are mean independent, these two parameters turns out to coincide. And this generates a huge amount of confusion when you actually have a reading causality. Because many times you get a statistical model that describes the statistical relationship between the variables, and you put statistical assumptions in the model to make the estimation of the parameters such as beta 1 consistently. And because you achieve statistical consistency, many times you think that you actually are dealing with causality. And you are not. And I'm going to make the case that to study causality, you need tools that are literally outside the realm of statistics. You cannot study causality, only use standard statistic. You need kind of additional tools to define causal parameters. This was just what I was talking about. The counterfactual outcome, y t 0, has to be understood as a thought experiment. I'm getting the variable t and fixing to a value little t. I'm getting the variable u, an observer that's fixing to a value 0. And with that, I get the beta 1, beta 0 plus beta 1t. While the conditional mean is simply a mean of the variable that for which all the standard statistical rules apply. In this case here, we use it an operation that is literally outside statistic, because in statistics use the the structure of the joint distribution of the variables to estimate parameters and to describe these variables. In this case here, we're actually manipulating the model by fixing the variables to values that we would like to estimate to evaluate. Okay. Now the concept of citrus parables is based again in the causal operation of fixing, and fixing differ from the statistical operation of conditioning. Again, this is it's often the case that in economic papers they start the model with an econometric model that just can relate variables in a standard statistical framework, and many times they take this econometric model as the causal model that's behind the data. And that is fundamentally wrong. The causal model behind the data is the causal model that defines causal relation between the variables. And after this model, you're going to see that you have kind of two procedures. One's the identification, then estimation. And this is actually different than actually writing down a statistical model and estimating the statistical model and using assumptions that allows you to get consistent estimation of parameters. In economics, there was a big confusion because sometimes economists define statistical models to define causality. One great example of this is the diff and diff estimator. The diff and diff estimator was a pure statistical model that people can confer one interpretation of causality to the model. And was only recently, in the last 5 years, that people actually studied the causal content of the diff and diff estimator. I do not know if you heard about Granger causality. Granger causality is another definition that's used by economists. That's not really causality. It's really a word that defines statistical relation of variables. Granger causality is a test that people get two variables and evaluate if one variable is explained by the both variables are associated with time, both variables are time series, and they evaluate if one variable is explained by the previous values of a second variable or vice versa. And using this test, they define which variable cause each other. Now, just to make this thing a little bit more clear, that statistics is actually different from causality, I put here four linear models to give a glimpse of the difference between them. Observe the first model. The first model I'm using a linearity. And in all this model here, the error terms are statistically independent. And in this case here is a model that I have kind of a t that's just a function of an error term. So we say that t is exogenous. It's just kind of the realization of t is just given by chance and is governed by this error term epsilon t. U is the same thing. It is exogenous and is determined by an error term epsilon u. Now, because the error terms are statistically independent, t and u are statistically independent. And the causal model that I'm writing here is the same. I'm saying that t and u causes y in a linear fashion. Okay. In this case here, we have a standard least square regression in which the error term u is statistically independent of t. In this case here, you can use linear OLS, ordinary least square, to estimate beta, and beta will be the causal effect of t on y. Now the other model here, I'm just going to change the causal link between the variables. In this case here, I inserted a different error term, epsilon v, that's going to cause jointly t and u. Epsilon, epsilon e is often termed as a confounding effect. It's an unobserved variable that is causing both t and u. And because it causes t and u, you make a t and u not statistically independent. So I have a dependent structure between t and u. And in this case, if you're going to apply the least square regression, because t and u are not statistically independent, the estimation of beta is going to be biased. So I'm not going to get beta. But beta in this model here is still the causal effect of t on y. Now, this model here, I again change the causal link between the variables. In this case here, I have u, which is exogenous. It's just generated by the error term. And then I'm saying that u causes t. Statistically speaking, these two models, the model 2 and model 3, are exactly the same. Why? Because t and u are not statistically independent anymore. They have a statistical structure between them, then create a co-movement between them. Again, beta cannot be estimated by least square regression. The least square regression gives a biased estimator. And in this case here, look, it's u causes both u causes t and t and u causes y. In this case here, beta is also the causal effect of t on y. Now I'm going to change the model once more. And in this case, I'm just going to change the causal structure. In this case here, t is going to be exogenous, and u is going to be caused by epsilon u and t. And the linear model is exactly the same. And because of this, because t causes u, u and t are correlated, and because they're correlated, the estimate of beta is going to be biased. But the interesting fact here that beta in this linear model here is not the causal effect of t on y anymore. Why? Because now t is causing y directly through b, but it's also the case that t causes u, and because u causes y, t is also causing y through u. So in this case, by just changing the causal link between the variables, we have three models. In one, you estimate beta consistently, and it is the causal effect. Then you have the other two that you cannot estimate beta consistently, but beta is still the causal effect. But the last one, you also cannot estimate beta, but beta is not the causal effect of t and y. So the statistical description of data and statistical model does not indeed kind of give you causality. You need to have a previous structure that defines the causal link between these variables for you to get a causal interpretation of the parameter. That is just a very simple example that illustrates this fact. Now,
All right.
again,
So let me drill down to this thing, because this is, I'm trying to disentangle the syntax of how you express these models to the, I guess, real world experiential thing, which I think you associate with causality, because it seems like for the way in this account, statistics is the computational procedure for estimating a model from biased data. And when you want to point at causality is kind of what buttons you would press, like how I would interact with the system in reality, and this is an encoding of my interactions. That's right?
I would say more. Imagine that I have a set of variables, okay? In the set of variables, without causal assumptions between how these variables behave, you cannot estimate a statistical model and ascribe causality, any type of causality, to the parameters that you extract from the statistical model. When you're doing causality necessarily needs assumptions about the causal link between the variables. So in this case here, I have kind of the causal link between these variables here is that t and u do not cause each other, and they are statistically independent. So the statistical model, well, you can apply standard statistical model and get estimate the causal effect between t and y. All the other models, it's not the case that you can get a simple statistical model, but imagine that you're going to improve the statistical model and you can get a consistent estimate of the beta parameter somehow, okay? Even though you can get the consistent estimate of the statistical parameter beta, it's not the case that the beta is going to have the same causal interpretation. In the second model, we have a causal model in which you have a confounding variable that affects t and u at the same time. And in this case, beta has a causal interpretation of being an effect of t and y. In the third model, I say that I put a causal structure in that U is exogenous, but U causes T. And in this case, the beta is still the causal effect of T and Y. And then I simply shift the causal link between the variables. Now, here I have T is exogenous and U and T causes U. And then I have Y is caused by T and U. And in this case here, the beta does not capture the causal effect of T and U because you also have to account of the causal effect of T on Y that pass through U. And the only difference that I did here was just changing the causal link between the variables, nothing more. If you are only going to use a statistical model that relates Y and T and U in a linear fashion, all these model 2, 3, and 4 have the same property. You have T is dependent with U. However, because of the causal link that you have behind this, you have very different interpretation of the beta parameter that you're actually trying to estimate.
Okay, no, this is making sense. So it's
Put
in order to make a causal, implication based on in this analysis, you need to know more about the underlying system. And maybe one way of making this kind of tangible, I think that's what I was missing, is if you have an underlying, let's say my model is a complex differential equation of motion of gases through a room. If all I have is statistics, it's hard to know what causes what. Do I, to make
especially in physics. For example, in physics, you have Bertrand Russell, for example, has kind of a very important paper that says that physics does not have causation, because in physics you actually get you get relationship laws that simply apply. For example, laws of gravity. You cannot say that it's actually kind of the Earth that's actually causing Moon to rotate around Earth, because Earth is actually causing the gravity, or is the Moon that's causing the gravity towards Earth and orbiting around Earth. It's simply a law that applies to both terms. So, like the gas that you're saying, you can describe statistically a system of particles like gas. But for you to get causality, you have to go one step back and actually have defined the assumption about the causal link between the variables. And defining the assumption of causal link between the variables is going to be essential for you to interpret it, to give causal interpretation to the parameter that is made from a statistical model. So causality is something that comes before the statistical model, and how you think about causality is going to define the causal interpretation of the statistical model that you estimate.
Well, so now let's go with this, because this kind of gets to what any of this is for. Let's say Earth Moon system. That's a great example because these are two objects that are causing each other. So would you have to just say Earth causes Moon, and given that make implications, or is there something about the gravitational equation that allows you to say Earth causes this, Moon causes this, and you can derive the causal structure from the underlying equations?
Look, in the case of physical system, that's a quandary, because the case of physical system, this system specific, you cannot talk about causality in this one, because this is a law, a physical law that applies to all bodies, and it's not the case that one body is causing the other or vice versa. It just exists for both bodies.
But if I were to move the Earth slightly, that would have an effect on the Moon, which would then have effect on a future Earth. So there is a notion.
Oh, okay. But now the causal link here is a little bit different. It's not the Earth is causing Moon or vice versa. As you have a system, and you're going to do a perturbation on the system. And the perturbation of the system that I'm going to get the Earth. But then the causal link that you're saying is that, hey, I have a system that exists, and I'm going to actually have to change a variable of the whole system. It's not the case that I have kind of causality to one body on another. I have a law that applies to both of them.
But my variable is the position of a portion of the system, the Earth. But you're right, it is a system always.
Yes.
But I can change anything. I can break up the Earth into two pieces.
Yes. In that case, yeah. If you you have a system, you have kind of a variable. A variable is the Earth in the system, and then we're going to kind of change this variable, the Earth, okay? And I'm going to have a cause effect on the system. But it's not the case that is actually kind of the Earth is causing the Moon. The relationship between Earth and Moon is given by a law. What you are actually changing, you are manipulating the distance between the Earth and the Moon, and changing the whole system. But you are not actually kind of defining that one is causing the other. But then you have a system that occurs, and you're perturbating the whole system.
Okay, very good. So now in that model, if I unroll the time series of realization of a differential equation, that would be kind of your causal models in this picture. And you can have, given essentially differential equations or their unrollings in time, you can say that this change earlier causally affects this change later. And here's a statistical estimation procedure for quantifying this change. But you have to have that underlying causal model.
Yes,
As a
yes,
summary?
yes, yes. That's great. For example, in the case of you just put it differently, there is no, you cannot say that the gravity is caused by Earth. You just say that there is a system, there is a law that gravity that applies to the system, and you can perturb the system itself. And then you get causality by perturbing the system itself, but you cannot assign direction of causality between the Earth and the Moon. It's not the Earth that's causing the Moon, or vice versa. You have kind of a system that is perturbing the system.
Oh, now that we're talking about this, how is that different from the derivative of the time evolution of the system?
Look, for example, we cannot the derivative of the time evolution of the system is just a statistical description of how these bodies actually kind of move.
Mm-hmm.
So for you to have any sort of causality, you actually have to define first. You have to define what's the variable that you control, and then you have to see what's the variable that I'm actually kind of perturbating, and then all the causality will be kind of all the things that occur in two counterfactuals, one that you do not perturb the variable and one that you perturb the variable, and you're going to compare these two.
Okay, so I think what you're, well, how is that different from a derivative? Because the derivative is roughly the difference between those two.
Great part. The derivative. Imagine that you have the difference. Okay, there are zillions of ways for you to compute the difference. So, for example, you have the average treatment effect. If your control variable, the change, is actually categorical, it's unit, for example, like we have here. When I change 1, so I go from t to t plus 1.
Mm-hmm.
Then you change 1 unit, and what you get is the average treatment effect of t on y. Okay, when you change 1 unit, the derivative is just to say, hey, I have kind of a slope of this derivative here.
Mm-hmm.
The derivative is just kind of one way to compute causality. And you're going to see in a few slides that you do not have one or two ways. You have a range of type of different causal effects that you can compute. Being
Great.
the derivative just one of them.
Okay. Oh, yeah. Excellent. So yeah, I'll stop.
And the derivative, you're going to see the derivative is going to be precisely what we call the marginal treatment effect.
Okay.
Okay. So just kind of to clarify the mind. So for you to actually do causality, do not start with a statistical model. You start with actually have to define the causal model that governs the variable. And this comes from statistical theory from the mathematical framework. After that, you do one on type of analysis with the identification of the causal parameters. And causal parameters you're going to see can be defined in different ways. And the identification is purely a mathematical analysis that uses hypothetical variation of the variable. And after that, you go from an estimation parameter, how to actually estimate. And it's often the case that you have a single identification structure, and this identification parameter can be estimated in a zillion of different ways. Guys, I already have used half 30 minutes. So I'm going to go a little bit faster. So what is the causal model? The causal model it has kind of 4 components. It has a set of variables, a set of error terms that are statistically independent, and you have structure equations that connect these variables. And these structure equations are often unobserved and non-parametric defined. I do not put any structure on these equations. Then these equations determine the causal links. Okay. This structure can be expressed like this. This is an example of a causal model. In which you have a variable x that's caused by v, and v also causes u, and x causes y. This is an equivalent representation of the model using structure equations or using a DAG. DAG is better because it actually has a visual connotation. And in this notation of the DAG, I put square for observed variables and circles for unobserved variables. Okay. Now, When you define a causal model, you have something quite interesting that occurs. If you define a causal model with a set of variables, a set of independent error terms, which by the way, it's not a binding assumption because you can always define unobserved variables to capture the dependency structure of the model that you're examining. Then you have this property that's called Bayesian networks. What are Bayesian networks? These are tools to translate the causal link between the variables into statistical independent conditions. And there are two major causal Bayesian network tools. The first one is called local Markov condition. It's a very simple tool. It says that one variable, say y, is statistically independent of its non-descendants. I mean variables that are not caused by y, condition on its parents. Just to give an intuition, so that's y here. What would be the parents of y? These are the variables that directly cause y. That's going to be x and u. And it's going to be statistically independent of its non-descendant. Well, non-descendants are all variables that are not descendant of y. Well, all the variables here are non-descendant of y because y is not causing anything else in this model. So y, the non-descendants are going to be v, x, and u, but v, x, and u are the parents, so we only left with v. So using local Markov condition, we have that y is statistically independent of v, condition x, and u. And you can do the local Markov condition using the rule for each one of the variables in the model. Okay. And then, if you apply the local Markov condition to each variables in the model, you get a set of condition dependency relationships. And then with the set, you can apply these graphoid axioms. They are just axioms to manipulate condition independent relationships in the model. So for example, I'm going to examine the second one. It says that when a variable x statistically independent of w, condition yz, and the same variable x when it's independent of y, condition on z, so I just got rid of w and put z instead, then it implies that variable x is going to be statistically independent of w and y, condition on z. Now you can see that you have here 6 rules. You can start with a set of condition-independent variables and generate much more by applying these rules until you generate all possible statistical independence variables in the model. So a causal model is pretty much defining statistical independent relationship between the variables that you are assuming. Now, what will be fixing? Fixing, you have a causal model here. You are going to fix a variable x, for instance, to a value. So instead of using y as a function of x and u, I'm going to fix the input x in the variable and create a counterfactual yx. Okay. Now, when I fix the variable, then I can create one causal parameter. For example, the average treatment effects, the expected value of y when I fix x to different values. If you'd like to get the derivative, it's simple. You just fix that variables to x and x plus epsilon, and then divide this parameter here for epsilon and do the limit of x going to 0. So you have a derivative, which is indeed a causal parameter. Is going to be the marginal treatment effect. Okay, so it's the treatment effect when you change a little bit only on x. Okay. Now just to fix, so the causal inference, we do need to get a directional causality between the variables. Why? Because when you fix a variable, you do not interfere on the variables that are not caused by these fixed variables. For example, in this model here, when you fix x, you are not going to change the distribution of v and u. You are only going to change the distribution of the variables that are descendant of x, in this case here, y. When you condition on x, it's a different story, because conditioning is a statistical operation that changes the distribution of all the variables at the same time. Because when you condition x, you change the distribution of v, that changes the distribution of u, and also change the distribution of y. When you fix x, you only change the distribution of y. So fixing is a different operation than statistical conditioning. And that, again, creates a huge amount of confusion in examining causality. Now, to solve these confusions, people create these causal languages. And the causal languages are just appendix of the standard statistical theory, just to cope with this operation of fixing that is not well defined in statistics. Again, because fixing is not conditioning. And there are many causal languages. The most the most famous one is this causal language called language of potential outcomes from Newman-Rubin model. I'm going to at the end talk about the hypothetical model that's a causal language to examine complex DAGs, direct cyclic graphs. And I think that you are aware of the do calculus of Pearl that also apply to direct cyclic graphs. Okay. Now, in economics, people most use the language of potential outcomes. Language of potential outcomes is a language that says the following: that it's based on independent relationships of counterfactuals. So it does not define the causal link between the variables, does not define the structural model behind it. It goes directly to independence relationships on counterfactuals. Let me give an example that make it simple. So this is a very important model in economics. Okay, it's a simplification model that captures a core principle, which is the matching models. Matching models are the following: you have a treatment or a variable that you would like to examine, and would like to investigate the causal effect of the treatment on the outcome y. Okay, and then you have some unobserved variables that impact the outcome y, but also impact some observed variable x. And this observed variable x impacts the treatment y. And this is the structure equation model. This is the direct cyclic graph. And this apply the local Markov condition to each one of the variables. And the local Markov condition just define it. One interesting feature: these three representations of the model are completely equivalent. They convey the same amount of information on the model. And they explicitly define some unobserved variable v that again causes both x and y. In the language of potential outcome, they were not going to use these structure equations. They are simply going to assume that yt is statistically dependent of t condition x, which means that if I have enough baseline variables that I'm going to control for, I can make the counterfactual outcome y statistically independent of t. And this is called matching assumption in economics, and there are zillions of variations of these matching assumptions. That is just kind of the simplest model that convey this idea. So in the language of potential outcome, they are going to use only this and not this structure. And interesting, the language of potential outcome is also equivalent to specify the model in this way, using structure equations. Now, the second most important model in economics is the instrumental variable model. By the way, this model here is identified, the matching model. You just need to condition x, and to get the causal effect of t on y, you just do the expectation of y condition on t and x. As soon as you have x, it's as if you had a randomized control trial occurring, so you can estimate the causal effect of t on y. The
Well,
second model.
is that the
Go
same
ahead.
assumption as like two-stage estimation and diff and diff and so on?
They are all, let's say, propensity score matching, standard least square regression. Whenever you have kind of a simple regression that people can estimate and get kind of a parameter data, deep down they're using matching, even in diff and diff. Even diff and diff have kind of a matching and also a parallel trend assumption, but the core feature is matching, which is a very, very strong assumption.
Excellent, got it.
Now, the second model most used in economics is an IV model. And the core idea is that you have an instrument Z, this instrument is an exogenous variable, and it affects the choice T. Now, the relationship between T and Y is confounded by the unobserved variable V that affects T and Y. Now, look, this model here, it's not identified. It needs additional assumptions to be identified. And most of the literature in the last 30 years in economics are literature to weaken the assumption that allows for to identify this model. Most important, if you know the do calculus, I mean, these two models get 95% of all the models in economics, okay? The other 10% are called control function model. That's pretty much a mixture between these two. So these two models are key. And the matching model is a good model, but kind of based on very strong assumption that, hey, conditional observed variable, I get causality. And the IV model is a much weaker assumption. I just need one sort of exogeneity. But this model here is not identified using it needs the additional assumption. So if you apply the do calculus to this model, it's going to say, hey, the model is simply not identified. And that's why the do calculus is not commonly used in economics. Why? Because it cannot identify the most basic model that economists do. Now I'm going to just show the difference between these two models that you can see in economics. In the language of potential outcomes, again, it does not use equations, and it defines the IV model as the following. You have something that's called exclusion restriction, that the counterfactor y, when I fix t, is the treatment, and fix z to z prime is the same. So pretty much says that z does not causes y, because I change z and the counterfactor is the same. I have the exogeneity, that the counterfactor outcome y and t is statistically independent of the treatment t. And these three models here, these three assumptions, they pretty much define the causal model. I need an additional assumption to be able to identify the model. And in the language of potential outcome, they use a monotonist assumption that says that when z goes from z to z prime, people are more likely, say, to increase their treatment. Now, you can write exactly the same model using a causal framework. In a causal framework, you define an outcome y, which is a function of the treatment t and an unobserved variable. You assume exogenate in this case here is just say that z is independent of the unobserved variables of the model. And instead of using monotonicity, you can use the equation of separability. Says that the t is an indicator that the propensity score, which is the probability of t equal to on condition z, is bigger than the unobserved variable u. It looks like quite strange, but these two models here are mathematical equivalent. They're exactly the same model, but just expressed in different ways. And one model here is much more palatable to understand. The other model is less palatable to understand, but they are based on exactly the same assumptions. But when you express the model using structure equations, you are allowed to define much more interesting causal parameters. And if you are using the language of potential outcomes, you can show that the two states square evaluates a causal effect that's called local average causal effect. And when you define the model using equations, you can define, for instance, the marginal treatment effect, which is associated with the differential that you said. Indeed, it's estimated by the expected value of y, condition t conditions equal to 1, condition t equal to 1 minus y condition t equal to 0, condition on the propensity score, and do the derivative of the propensity score. So by using the structure equations, you can define some parameters like marginal treatment effect. And the key feature is that in the structure equation, we actually have put a variable, u, that defines the unobserved characteristics. If you go back here, there is no mention of unobserved variable because the language of potential outcome does not use unobserved variables. However, when you do a structure equation, you have to define an unobserved variable. And by defining an unobserved variable, you are allowed to define different causal parameters like the marginal treatment effects, which is y1 minus y0, condition on the value of this unobserved variable. So a condition on an observed variable that we do not know, but it turns out that this thing can be evaluated. But most important, we can define a range of type of different causal parameters. This is the average treatment effect, y on the treatment minus y on the control, the treatment on the treated, the treatment on the untreated, policy relevant treatment effects. And then we can show that each one of these parameters can be written as an integral of the marginal treatment effect that we evaluated before, multiplied by weighting scheme. So pretty much, all the slides are to say the following. When you define a model using X kappa equations, you can define very interesting causal parameters. They're not simply the derivative or the average treatment effect, but a range of causal parameters, and you can express them, all of them, as the derivative of the causal parameter that Greg mentioned before, but just using different ways to get different parameters. Now, take home message is just that indeed using structure equations gives you much more powerful to examine causality instead of language of potential outcome that are commonly used in economics. Now I'm going to go to more of a Pearl type of analysis that you may be more familiar to. If I can, this is the front door model of Pearl. It's a model that have a treatment that impacts a mediator, that impacts an outcome, and you have an unobserved variable V that affects only the treatment and the outcome. What is the major causal assumption here that makes this model identified? I'm assuming that V does not directly cause M. So I got rid of this arrow here. In the language of potential outcome, this model is defined by this set of equations here, which does not give you quite of intuition. But here, it's defined as a causal model. From now on, we're only going to use causal model. Well, how are you going to identify the causal effect of T and Y on this model here? I'm going to pass this a little bit and give some intuition. So this is the front door model. Observe that if you are familiar with the Pearl type of analysis, the variable X block the effect of the confounding unobserved variable U on M. So condition X, I can get the causal effect of M on Y. Moreover, if you only examine X on M, there's no confounding variable between X and M. So I can get the causal effect of X on M. How to get the causal effect of X on M? Well, you just have to get the expected value of M, condition X, you have a causal effect. How to get the causal effect of M on Y? You have to condition X. Then I have the causal effect of M on Y. And how to get the overall causal effect of X on Y? Then you're simply going to estimate the causal effect of X on M, and then integrate this causal effect by the distribution of M condition X. It's pretty much here. I'm using T. So to get the causal effect of T on Y, I first compute the causal effect of T on M, which is compute the causal effect of M on Y, I'm sorry, condition T, which is this little guy here. So I just get all the causal effect of M on Y condition T. And I integrate this all to get rid of all the T's. So I simply get the causal effect of M on Y. And then with this causal effect of M on Y for each M, I just integrate out by the distribution of M condition on T. And that's kind of the identification of this model here. Now, what I'm going to do next is the following. I'm going to explain a causal method that applies to DAGs, which are general direct cyclic graphs that examine complex relationship between the variables. So for this, we are going to use some core ideas of Habermas, and we're going to introduce what I call the hypothetical framework. The goal of this framework, again, is just to get a setup that can be coded, and you can given an assumption on the causal relationship between the variables, you extract two solutions. One, if a causal effect of a variable T on Y is identified, and if is identified, what's the equation that identified this causal effect? Again, these type of models are not used very frequently in economics. And the model that we would like to do is a model that solves this problem of fixing. Recall that fixing is a ill-defined concept in statistics, because it's fixing a variable only affects the descendants of the variables. So it needs the causal link between the variables to define fixing. While in statistics, it only examines the overall dependency structure of the variables, and conditioning affects all the variables on a system. And the thing that we are going to do is the following. We're going to have a causal model, which is simply a definition of a causal relationship between the variables. And then we're going to create a hypothetical variable. And this hypothetical variable is going to break the link of the treatment on the other variables. And it's going to have a special property, which is going to be an exogenous variable. And I'm going to use an example that makes it clear. So imagine that you have a very simple model like this one here. So this is the model that you have an observed variable V that affects T, and also affects U, and U affects Y. Okay, this comes from the theory that we are using. From this model, I'm going to create a hypothetical model. And a hypothetical model, I'm going to break the link between T and Y and create a hypothetical variable, T tilde, that actually affects Y instead of T. Does this variable t tilde exist? It does not. It's just a way, again, it's a way of thinking. It's an uh, uh, abstract reformulation of the empirical model that generates the data. So this is the model generated data. This is the hypothetical model. Why the hypothetical model is interesting? Because by breaking the link of the treatment, I have some very interesting property here that this t tilde is an exogenous variable. And if I had this model, if the empirical data was generated by this model, I could get the effect of t and y by simply getting the expectation of y condition on t tilde. So again, the hypothetical variable t tilde replaces the t inputs of the variable. Everything else in the model is exactly the same. So the main benefit of creating this hypothetical variable is that in this hypothetical model in which I break the causal link between t and y and create this t tilde, the hypothetical variable, the causal effect of t on y is simply the expected value of y on t tilde. That's it. So what we did is the following. Just in a nutshell, we have the empirical model that may be as complicated as you want. We break the causal links between the arrows that emerge from t, and create a hypothetical variable t tilde that is exogenous, not caused by any variable in the system. And if we had this model here, to compute the causal link between t and y is very simple. It's just compute the expected value of y condition t tilde. But we do not have this ideal world here that's easy to compute the causal effect. We have the empirical model. How to identify the effect of t tilde and y? Well, the identification of this model, it relies on rules that allows us to connect the distribution of this hypothetical model with the empirical model. So the identification, this setup, is a game that we play that says we can define the causal model in this hypothetical model. How can we use this definition to match the distribution of this hypothetical model using the data generated by the empirical model? And for this, we need to create rules that connect these two models. And these two models, these rules are, there's only two rules that connect these two models. And these two rules apply to the hypothetical model. And the rule is the following. If I have an outcome y, statistical condition t tilde, condition on t, and whatever variable w that there is, then I can show that the probability in the hypothetical model pH of y condition on t is going to be equal to that probability in the empirical model of y condition on t. So I get one distribution that I want to estimate, that's y condition t tilde, and I equate this with the distribution of the empirical model that generated the data that I observe. In the second rule, I connect y. If y is statistically independent of t condition t tilde, I can connect also the hypothetical probability of t of y condition t tilde with the empirical probability of y condition on t. Let's just examine these two rules here. See, these two rules are very close related. The only difference that one I get the statistical independence of y statistical independent of t tilde condition on t, while the other one I have y statistical independent of t condition t tilde. So pretty much, if I have a causal model in which I have y statistically dependent of t tilde condition t, or y statistically dependent of t condition t tilde, I'm game because I can equate distributions of one model with another model. And with this, give me the possibility of identifying causal effects. Okay, now let me just give some example. So in this case here, we have the empirical model that is, well, V impacts T, U, and Y. So this is the model that generates the data, and this is my hypothetical model. In the hypothetical model, if you're going to apply the local Markov conditions, we get that Y is statistically independent of T condition T tilde V. And using this rule, I can show that the expected value of the condition or counterfactual outcome YT condition V, which is this variable here, is going to be the expected value of Y condition T and V. So pretty much says that condition on V allows me to compute the causal effect of T and Y. But now let's get kind of examples that are far more interesting. This is the front door model of Perl. So I'm going to apply this mechanism of hypothetical model. The first thing that I do, I break the causal link between T and M, and I create a hypothetical variable T tilde that affects M. Now in this model here, if I apply the local Markov conditions, I get a range of statistically independent relationships. And I would like to get statistical dependent relationships that associate Y statistically dependent of T tilde condition on T, or a variable that's statistically dependent of T condition T tilde. And these two statistical relationships here are hold in this hypothetical model. Again, to obtain them, we simply apply local Markov condition and graphoid axioms to this model here. Now, if I have this type of relationship that have T tilde and T, I can do something that's quite remarkable. I can identify the model. So for instance, in my hypothetical model, I have the Y statistically independent of T tilde condition T and M that comes from just analysis of the causal link between the models. And observe that here I start with Y and I have T tilde T. The next independent relationships is statistically dependent of T condition T tilde, and the last one is T tilde T. And I sort of bridge the variables. I start with the Y, and I wanted to estimate what the expected value of Y condition T tilde. And then I condition a set that has M, and it turns out that M also have these rules that are important for me, because M is statistically independent of T condition T tilde. So in simple terms, we start with Y and have a conditional set here, M. We would like to have a system, a sequence of statistical condition relations that have T tilde T, and then it flips T tilde, and so on. And it starts with Y and condition a set of variables, and the set of variables are included in the second independent relationship. It keeps going. If we have this type of system of independent relationships, then the model is identified. How it is identified? We start with the probability of, in the hypothetical model of Y condition T tilde, and then we rewrite this probability as a probability of Y condition on more variables, say M and T. And this is from the first line to the second line. I'm just using the factorization of the distribution, that standard distribution probability theory. So I start with Y T tilde, then I put Y condition M, T, and T tilde, then M condition T and T tilde, and then simply T condition T tilde. Now, these probability equations define a hypothetical model, the model that it doesn't exist. And I have to, but because of the statistical relationships of the model, I can connect the probabilities in the hypothetical model with the probabilities of the empirical model. And each one of these probabilities can be expressed as a probability of the empirical model. And because of this, I can identify the causal effect of T on Y. Why? Because I expressed the probability of T condition T tilde as probabilities in the empirical model that generate the data. And this is just a method for you to examine the identification of causal parameters in complex DAG models. I'm going to give two more, given that I already come out of time, I'm going to give two more examples just for you to get kind of a notion of this method for identifying complex models. This is just to say that the equation that I had before is exactly the same equation that we did using structural models. Imagine that you have this complex model here. You have a choice T, a treatment T, and it impacts a mediation 1, then a mediation 2, then a mediation 3, and then it impacts an outcome Y. And this model here has a very specific structure about unobserved variables, V1, V2, V3, that impacts each one of these variables. These variables in economics are called endogenous. Why? Because if I just get the regression of Y on T, I do not get the effect of T on Y. Okay. Now I'm going to, in this complex model, I'm going to apply the hypothetical model framework. first thing that I do, I break the causal link between T and M and put a T tilde here that impacts M. So this is a causal model. If it is a causal model, I can generate the local Markov conditions that give me a range of statistic-dependent relationships. And in those, I can apply graphite axioms that give more statistically independent relationships. And in this model here, I search for this set of statistical independent relationships. Again, you start with Y, and you have T tilde T, and it shifts them for T and T tilde, T tilde T, T and T tilde, and so on. So I start with Y, and because of the model gives me that Y statistically independent of T tilde, condition T, and a set of variables. The second relationship, I decompose the set of conditioning variables, M3, M2, M1. Now the model gives me that M3 is independent of now T, condition T tilde, M2, and M1. And then the third one is M2, statistically independent of now T tilde T, condition M1, and so on. So I have this alternating pattern of T tilde and T, and I can also list one observed variable that's condition on T or T tilde, that's independent of T and T tilde, condition on the other T and T tilde, and the remaining conditioning variables. And if I have this pattern here, that is a sufficient condition for you to identify the model. And again, the identification procedure is that you express the Y condition T tilde in the hypothetical model, and you condition a bunch of variables. And because of these statistical independence relationships, I can connect the hypothetical model with the empirical model and identify the model. So in this particular model, the outcome Y, the counterfactual outcome YT, is identified by this equation. And the identification equation always has a pattern that I'm going to sum over many variables here, and it has an alternating pattern that I have T tilde and T and T tilde and T. What is T prime? T prime is the variable that I'm summing over, and T is the counterfactual. T is the treatment that is associated with the counterfactual Y. And that is a nutshell, a method for you to examine the identification of causal parameters in DAG models. Now, the do calculus does exactly the same thing. And if the model is identified, it's identified even the do calculus also using the hypothetical model. But one very interesting feature that occurs is that the do calculus, even though it identifies the model and gives the equation that you gives in the do calculus is often different than the equation that you get using the hypothetical model. And it's quite surprising that all these equations here are equivalent. If you work out the math, you see that the equation that you have the top is equivalent to the equation that you have at the bottom, which is the equation generated by the do calculus. And now I'm going to get the last example. That's a Verma model. That's kind of a very famous model in the literature of causality. Again, you'd like to get the causal effect of T and Y. And if you go to this model, apply the local Markov condition, graphite axioms, you can generate 3 statistically independent relationships. Again, one starts with Y, condition T, this T tilde, T tilde T, then T tilde, and so on. And with this alternating pattern, that's the alternating pattern, Y, T tilde T, M, T tilde, X1, T tilde T, and so on. You can use this alternating pattern to identify the model, which again express the probability in the hypothetical model of Y condition T tilde, and it's a summation over T prime, M, and X1. And in each one of these probabilities, you can link them with the observer probability in the empirical model generated data. And with those, you identify the model. Now, if you put exactly the same model and use the do calculus, look the difference between the identification equation that you get from one method on another method. Both methods give you that the causal effect is identified, and both methods give you an equation that identifies the method. And this equation, believe it or not, it is equivalent. So in the hypothetical model, you get this simple equation here that identifies the model. If you apply to the do calculus, you get this very complicated equation here. And again, these two equations of the identification are equivalent. Greg, I went out of my time and I'm done here.
Yeah, that's
If you
fine.
have,
This is interesting. Let me just ask one thing to clarify. It seems like the thing that's kind of behind this idea, it seems, is, well, the difference between conditional dependence and causal treatment. Let's see if I can capture this right. Conditional dependence means that I say when this variable has this value, I look at the entire probability space, which is kind of the biased thing that depends on the actual dynamics of the thing. Yeah. And if I say it's the value is here, the value of this variable is this, that really constrains the values of all these other variables.
Yes.
And in the causal world, you say is, no. I have more information that's actually in this distribution. I know that I can stop the moon. I say I can't stop the moon. I can just intervene in these parameters. And I wanted to know that if I were to stop the moon, change these parameters and not affect everything else, what would happen? And
yes, exactly.
New question that's different from distribution.
Greg, and this is a core idea of causality. And you express this thing very well. And if you're going to get kind of one thing about kind of this presentation is exactly what you said, which is the following. Look, see this causal model here. If I were to condition on T, it would affect the distribution of all the variables.
Right.
That here it will affect V2, affect V1, the distribution of V1 that would affect X1. Pretty much when you condition on T, it affects the distribution of all the variables in the whole system.
Right.
Now, causality is not conditional. Causality is actually a hypothetical manipulation of the treatment.
And that's so, for example, that's your other model. That's your T tilde. That is literally me stopping the moon.
That's a T tilde. Oh, look, and if you did manipulate T tilde or condition T tilde, the only if you condition on T tilde, you're going to condition first M and then Y, and that's it.
No, and
so causal link just kind of.
I mean, all you've done, I think, and I'm trying to get the simplest formulation of what you've done. Is first of all, you said it's different to say conditional and conditional on the moon being in the spot versus I stop the moon and put it over there.
Yes.
And then you have a new variable, T tilde, which is, look, I ripped out the moon and shoved it over there. That is my graph representation of that action. And the moment you've done that, all the causes onto the moon go away. You have, in a video game, moved it over there. And now your causal structure is so much smoother because it's just a chain of causality you can just condition on.
Yes.
Easy.
Exactly. Well, in the moon concept, imagine that you have a program that actually can get rid of the moon over there. Say, hey, what happens if the solar system gets rid of the moon? Great. And then the solar system is going to happen something. Now, if we're conditioning, let's make a parallel. Would be imagine that to get the moon, I'm going to get the moon and extract the moon slowly to other solar system. And that will have a huge amount of consequences in the solar system.
Yeah.
Now, in the causality, I actually can put the moon and get rid of the moon without kind of all the effects that in between that are generated by the causal link, which is given by the dependency structure of the data.
And your analysis becomes much easier because all the causal links, all the annoying causal links are gone. Just the ones you care about remain.
It's more than that. It's not it might become much more complex, but the key feature is that when you do that, you are actually getting the causal effect of one variable to another. Another example is the following. Oh, imagine that you would like to get the causal effect of schooling or going to college or not. You cannot see just by observation that people who are, say, smarter go to college more often than people are not smarter.
Yeah.
So the observational data will not give you the causal effect of going to college. So then you can do this using an IV model that gives some sort of exogeneity. But given the sort of exogeneity, how am I actually going to use this exogeneity to get the causal effect of going to college or not? And then you have to use a causal model to get the equations that should generate what type of equations allow you to estimate this causal effect. It's not that it becomes easier, it allows you to see, is it identified or not? And if it's identified, what's the equation that identified it?
Okay, I think it's making sense. And I guess IV is the analogy is you have randomness in the in the world. I mean, like lottery numbers and whatnot. And you're not allowed to just pluck somebody and put them in a different situation, but you're looking for real world scenarios like lottery numbers that actually do that, and you can extract from that.
Exactly.
Yeah.
Say, okay. So in the case of IV model, look, this is the IV model. What would be the hypothetical one? I would break this causal link here. We'll put a T tilde affecting Y. Okay. That will become my ideal word in which I get the causal effect of T tilde on Y. Okay. Now this word does not exist. That's all right. How can I use the actual word that have some exogeneity here, and I use this exogeneity to be able to evaluate the causal effect of T and Y? And this exogeneity is not the best exogeneity. It's not say a randomizer control trial, but it's one source of exogeneity. How can I manipulate this exogeneity and extract exogeneity to get the causal effect of T and Y? And for this, you need a causal model behind for you to explore this.
Okay. No, that makes a lot of sense. Yeah. Thank you very much.
Thank you very much, Greg.